Hello, I am Aman, a second year grad student in the Department of Material Science and Engineering at Pennsylvania State University. I am working on developing new compositions on piezoelectric application. So I mostly work on lead-free piezoelectric ceramics. So in today's discussion, I will be basically discussing on piezoelectricity and piezoelectric material, followed by synthesis of piezoelectric material, the steps and the process in detail, what I use at lab. And finally, the piezoelectric material application, which will be very interesting, the medical application, electronic application, and day-to-day life application. So starting with what is piezoelectricity? So the piezoelectricity effect is very simple. As you can see in the video, when we are applying an external stress to the crystal. So this disc-shaped crystal is a piezoelectric crystal. When we're applying an external stress, when we are squeezing the crystal, it is changing its shape. A voltmeter is connected to the output and it is showing some value. So this is piezoelectric effect, like a voltage is induced when you apply an external stress to the crystal, and vice versa also exists. That is, when we apply an external electric field, the crystal changes its shape. It is known as converse piezoelectric effect. And for application in day-to-day life, we use both the theories, converse as well as direct piezoelectric. So it was first developed by two French physicists, Jacques and Pierre Curie, in 1880. And they somehow observed the accumulation of electric charges on the surface of few material when they apply stress, or when they started bending the rods, they started seeing the sparking on the surface. So that's how they started developing the theory of piezoelectricity. So going into detail, what is the difference between a piezoelectric and a non-piezoelectric material? I mean, what is there in the piezoelectric material which is making this difference, which is inducing voltage when it is under the stress? So the first figure describes the different unit cell of a non-piezoelectric crystal, which is centrosymmetric, and it has its center of positive charge and negative charge coinciding, and they're canceling out each other. Even if the same configuration we're observing when the crystal is under the stress, when we are squeezing the crystal. But in piezoelectric material, when you start applying the stress, the center of positive charge and negative charge start moving apart, forming a dipole. Finally, each unit cell develops one dipole, and there are hundreds and thousands of unit cells developing hundreds and thousands of dipoles. And finally, we can see a small difference of voltage across the crystal. That is how the voltage is induced in the stress. So the very basic way of defining this is in lab is by doing a tapping experiment on LED. So this is an interactive video. I'll play it for you. You can learn how to define the piezoelectric effect in lab, how we can identify whether a crystal is piezoelectric or not by just putting up an LED.
The American Ceramic Society and the Ceramic and Glass Industry Foundation are pleased to provide you with this instructional video for the teacher-led demonstration, Piezoelectric Materials. The objective of this lesson is to demonstrate the piezoelectric effect in several materials and explain why this property exists in certain materials. The piezoelectric effect of a ceramic disc and a polymer film will be demonstrated through the use of LEDs. Some of the materials used in this lesson are included in the Materials Science Classroom Kit, while other items will need to be purchased. Those items are commonly found in grocery or department stores. In some instances, it is appropriate for students to bring some items from home, which helps pique their interest. The materials needed for this demonstration are 2 piezoelectric ceramic discs, 2 piezoelectric polymer films, 4 light-emitting diodes, LEDs, 8 alligator clip sets, voltmeter, musical greeting card. Connect one LED to a piezoelectric polymer film so that one wire of the LED is connected to one leg of the film and the other wire on the LED is connected to the other leg of the film. Use the supplied alligator clips to make these connections. Then connect one LED to a piezoelectric ceramic disc so that the long wire of the LED is connected to the red wire of the disc and the other LED wire is connected to the black wire of the disc. With a very light tap, slowly increase the force until the LED visibly flashes with each tap. Show the effect to students. It is important to simply tap the disc and to not apply steady pressure. The room must be fairly dark to see the LED light. The LED light flash has been enhanced for this video. Then bend the polymer film back and forth slowly. Increase the speed at which you are bending the material until the LED lights up with each bending motion. Again, the room must be fairly dark to see the LED light, and the LED light flash has been enhanced for this video. Open the musical greeting card and explain the use of the piezoelectric material as a speaker. Take apart the card so that students can see the actual piezoelectric buzzer. If time allows, an additional activity with the materials can be performed with a voltmeter in place of the LED to measure the voltage generated by the piezoelectric. This provides a better indication of the piezoelectric effect, as the light generated by the LED is very minimal. Connect the two piezoelectric materials in series and try to generate more voltage by simultaneously activating both materials. Consult the teacher's manual included in the Material Science Classroom Kit for discussion questions to ask.
So it was an interactive video of how we can determine the piezoelectric effect in polymer as well as the ceramic crystal. So as you have seen, the LED was blinking when the person in the video was tapping the ceramic crystal, but in the case of polymer crystal, he had to bend it. So it has different mechanism on different type of crystal, how we are inducing the dipole and how we are applying the stress depending on that, the piezoelectric properties working. So moving on to the type of piezoelectric material. So we have quartz crystal, PZT piezoceramic. So PZT is basically lead zirconia titanate. We have barium titanate followed by lithium niobate, sodium potassium niobate, potassium niobate. So the most of the commercialized application of piezo are on PZT ceramics. So PZT is lead based. As we know, lead is quite toxic and heavy, and it is also not good for environment as well as for human health. So nowadays, most of the research is being carried out, is being focused on lead free, because we need to shift from lead based composition to lead free composition for environment friendly as well as health friendly. So these are the class of material. Moving on to the synthesis of piezoelectric material, we follow solid state synthesis reaction. So all the reactions that takes place in the solid state for forming substitutional solid solution. So we start by weighting out the powders. So let's suppose we are making PZT, lead zirconia titanate. We have different oxide. We have lead oxide, zirconia oxide, and titanium oxide. We weigh out according to the composition we need and ball mill it. In ball mill, we mix the powders properly. Then we calcine it to form the appropriate phase, the appropriate composition. Then again, we ball mill it after calcination to nanostructure the particle, to chop down the particle to smaller particle. So after that, we form compact disc or compact or cylindrical shape ceramics. Then finally, we sinter it at very high temperature to increase the density. So the density of those ceramics has to be very high, and the temperature we use for sintering is very high. It's almost 1000 to 1200. These are high temperature furnace, and we carry out this experiment at air ambient. Then finally, we polish down the ceramic. We electrode it with a conductive uh, paste like silver paste or different kind of conductive paste. And finally, we carry out all the piezoelectric measurements, like the strain measurement, the D33 measurements, the KP measurements, the frequency measurements. So there are a lot of measurements which we do on the ceramics. So that's all are being all carried out after electroding the ceramic disc on both the sides. So moving on to the application part, the first one is the application in medical science, like the day-to-day medical diagnosis. So I'll not play the video fully. I'll only play the part where he's explaining the application as of piezo disc in stethoscope. So it will be an interactive application.
Electronic stethoscopes can convert sound waves to electrical signals which enable them to listen, record, and play back sound waves coming from the body. One of the most popular ways used to convert sound signal to electrical signal is using a piezoelectric material. The special property of piezoelectric material is that when external stress is applied across the material, it can generate voltage. Let's take a look at how these materials are able to electronic stethoscope has a very thin diaphragm connected to the piezoelectric material. When the sound waves hit the diaphragm, it oscillates, making compressions or expansions in the piezoelectric material. This produces voltage across the material proportional to the amount of deflection. The voltage is then transferred to an amplifier and filter circuit to get the desired output. We connect the piezo material to a foam spacer and a steel plate to enhance the vibrations, which in turn results in generating more voltage. Thank you for watching the video. See you next time.
So stethoscope is very commonly used in all the medical. Before you go for a checkup, the doctor check your heartbeat and other things through the stethoscope. So it uses a piezoelectric ceramic disc and it is widely used in all the hospitals. So moving on to next application in the medical in the hospitals is the ultrasound detectors. So which we use to detect tumors at different parts of body and other things. So here also I will play that
The
part of video
piezoelectric transmitter
which will explain the mechanism of detecting the tumors and the foreign bodies which are growing at special parts of our body.
receiver or transducer. This is the part of the body under investigation, and a gel is placed between the transducer and the body to prevent reflection of the ultrasonic waves at the skin. Here we have the piezoelectric crystal with electrodes either side attached to a cable which will be connected to the computer. A brief alternating pulse is sent down the cable, causing the piezoelectric crystal to contract and expand. This sends out an ultrasonic pulse which will travel into the body. The reflection will travel back, again causing the piezoelectric effect, producing an alternating voltage. This can then be picked up by the computer and interpreted. Bone, sugarcane and many other materials show the piezoelectric effect, but other man-made crystals such as lead zirconate titanate are used in the ultrasound transducers. By making the crystal a whole number of wavelengths in length, resonance occurs and this increases the effect.
So bone is a very good example of organic piezoelectric material. As we are in the growing stage, so we do more pull-ups, our height increase. So that is an application of that is a good example of piezoelectricity. So moving on to electronic application. So piezoelectric actuators are widely used in many applications like video camera, smartphone, and barrel machinery. So actuators use converse piezoelectric effect. When we apply an electric field, they either contract or expand depending upon the polarity of field. So I'll explain this in more detail when I'll go to the inkjet print, the nozzle of the inkjet printer part. These are also used in speakers and buzzers. So this is a very basic design of speaker and buzzer where you have a silver electrode paste printed on, painted on a piezoelectric ceramic disc, and this disc is connected to a brass membrane. As we apply an alternating electric field, the disc starts vibrating, and this vibration is transferred to a brass, and finally, this acts as a buzzer. So this all we use in our calling bells at home, and other application also is there of buzzer. So this is the nozzle of an inkjet printer. So uh, there is one piezo element here, piezo disc here. When you apply an external voltage, the disc changes its shape, and depending on the deformation, the ink particle are ejected out of the cartridge. So this is a very good application in our day-to-day life. And piezoelectric motors, crystals are preferred for the application that require precise accuracy. These are also used in few robotics application for controlling the movement of a motor. And finally, the sensors. The sensors are knock sensors and the gyro sensors in our phone, the accelerometer sensors in the cars, and all those stuff are piezo sensors. So this is a very good interactive video where you can see that how can we use piezoelectric crystals for as an energy harvester, and how can we use it in our day-to-day life.
Some things only work when they're hit on. One of them is a special sort of crystal that yields electricity when squeezed. These piezoelectric crystals can be found in lighters for kitchen stoves, in machinery for baby ultrasounds, and in sonars used by ships to measure water depth.
Millions of people rely on pacemakers or other electronic medical devices embedded in their bodies. But changing batteries can require surgical procedures, which can have complications. But post a battalion of piezoelectrics under the skin in a capsule next to the battery. Now all you need to do is make them vibrate. And you can do this with a special device that rests against the skin. It vibrates at just the right frequency, and the waves it generates pass harmlessly through the skin, charging the battery. Finally, as engineers make new advances, this piezoelectric army will travel with us. New fabrics and shoes are being set up with these super useful crystals. They're ready to do the work of charging batteries in small devices that are more and more becoming part of our lives.
In your car, they trigger the sensor that decides when to inflate an airbag.
On your desk, telling your hard drive how to read and write data.
In your home, that clicking noise is physical motion being turned into an electric spark thanks to piezoelectric crystals.
And those catchy, sometimes annoying tunes in kids' toys, a tiny little circuit powering a piezoelectric speaker.
Researcher Beatrice Nojeda of Groningen University wants to use them for something different, generating energy. For example, you could use piezo crystals in a dance floor, which will generate electricity while you dance. Not enough to light a whole city, but you could certainly power the dance floor lights. A bit more useful would be using the crystals to generate energy in spots where it's not so easy to use an extension cord. Within a car tire, for example, where a tiny sensor measures the air pressure. Using a piezoelectric crystal, you could use the tire's vibrations to power this sensor. Or maybe you could use piezo crystals to power a pacemaker, making use of the thumping of the heart itself. However, there is one problem. The best available piezo crystals contain lead, which is poisonous and ecologically harmful. So, Beatrice Nojeda wants to find piezo crystals without lead, which are just as good or better than the lead-containing ones.
One of the most revolutionary uses is in something called structural health monitoring. Think of a bridge or an airplane wing. We need to know they're structurally sound before we use them, but inspecting them on a regular basis is difficult. That is, until you call in the piezoelectric army. Since large structures like these move or vibrate a tiny bit, they can supply just enough motion to piezoelectric crystals, which can then power sensors that can tell us whether the object is safe and sound.
There are a lot of fascinating challenges in piezoelectric field. As you can see, the application part, we can think of developing more and more better transducers. We can play with the design of the transducer so that its performance can increase. On the material part, we can work more on developing lead-free piezoelectric. So it's really fascinating working on piezoelectric ceramics, and it has a lot of challenges which can be solved and which can make the material and the application even more better than
Some things
existing one. Thank you for your kind attention. Hope you have enjoyed it. Thank you very much.